All right. Good morning. This is your Stat Sensei, Mr. Spensei, and this is a pre-quiz on chi-squared. So this is scenario one. It's your birthday. While conventional wisdom suggests that births should be uniform throughout the year, some medical professionals speculate that factors such as seasonal conception trends, holidays, and healthcare access may cause fluctuation in birth rates across different months. To explore this, a group of public health researchers collect birth records for 1,220 randomly selected newborns. All right, so it looks like we have a sample size here of 1,220 from hospitals across the country out of the more than 3 million babies born last year. So it looks like right here we have a population. All right, the data is found in the table below. So we have 100 born in January, 90 in February, et cetera, so on. Out of 5% significance levels, are births unevenly distributed across the months? So that's where we begin. So the very first thing we need to do is go ahead and enter that data into stat edit, which I have already done. And since we're trying to see if they're divided evenly, I just filled one all the way down, but I'm going to divide that by 12. So blue 2 divided by 12 tells me I should have about 0.08% of the births in every single month. I need to take that and I need to go, the expected value is going to be the sample size times the probability. Well, our sample size in this case is 1,220, and our probability, we just put that in a calculator. So we can go blue 2 again times 1,220. And it turns out that we're going to have an expected value of about 101.6 births. And because of room, I'm just going to call it 101.6, probably closer to 101.7. So if you put 101.7, that's fine. All right. Our formula, of course, is chi-squared equals observed minus expected squared over expected. And so we now have our observed, we now have our expected. In fact, we could go ahead and plug into this thing, but I'm inclined to go ahead and run the test. So let's do that. So stat test chi-squared goodness of fit, L1, L2, and our degrees of freedom, we have 12 categories minus 1. And we do that and we get a p-value of 0.0302 and a chi-squared of 21.3. So that's going to look like this. We're going to start at 0 and we're going to go all the way to positive infinity. Our chi-squared value is 21.3 and our p-value, our shaded area, is 0.0302. All right, as we look at plugging in, we have our observed of 100. That's for January. And our expected for January is 101.6. And then for December, we were observed 90, but we expected to have 101.6. All right. And then we ended up with our chi-squared value of 21.3. And there's our calculation for our degrees of freedom. So chi-squared goodness of fit. And we kind of got that off the calculator anyway. Stat test, chi-squared goodness of fit right there. So the null hypothesis. Each of the month has the same number of births. Keywords here are each and same. All right. The alternative is at least one, that's the key phrase, at least one of the months does not have the same. All right. Does not have the same number of births. So basically, our null and alternative are exact opposites. So our conditions, we had to have a random sample. When they told us they had a random sample of 1,220, and that was given to us. The next thing is we need to make sure our sample isn't too big, and we do that by multiplying by 10. We go 1,220 times 10 gives us 12,200. But that's still less than a 3 million births, so our sample size is less than 10% of the population. The next thing we have to do is make sure that the sample is actually large enough. Well, in this case, we always say all expected values are greater than 5, see table. Well, was that really true? Yeah, it actually was. Our expected values in this case, all of them were the same. They were all 101.6. So they were definitely big enough. Continuing on, we have our probability statement. Well, I can pretty much take our probability statement straight from our graph. The probability that chi-squared is greater than 21.3 equals 0.0302. And our alpha, which is what I have right there. And our p-value of 0.032 is less than our alpha. So our decision is to reject the null. So our conclusion is going to be simply this. We're going to restate this in sentence form. Basically, our p-value of 0.032 is less than our alpha of 0.05. We reject the null. And that's certainly what I wrote. Our p-value is 0.0302, which is less than our alpha 0.05. We reject the null. There is sufficient evidence to suggest that at least one of the months does not have the same number of births. Please remember, this part right here always comes from the alternative hypothesis. And our alternative hypothesis was at least one of the months does not have the same number of births. They're exactly the same thing. All right. I appreciate you for watching. Look forward to seeing you on the next one. Thank you.